Welcome back. We will now continue our discussion on atomic force microscope, and we will discuss how the images actually get generated. So, we are building our fundamentals step by step. First, we discussed what are the hardware elements, what are the key operational aspects, and then we got into some bit of details, and in the previous class, if you remember, we discussed the sequence of approach. So, now we have an atomic force microscope which has sort of approached, and therefore, the piezo is now active, and so is the feedback loop. So, the configuration of the cantilever is like this. It is in the repulsive regime, and the reflected beam is now falling at the set point location, okay, and it is in contact with the surface. So, this is now an approached AFM. Okay. And based on this, now the scan sort of starts. So, this is a quick recap. So, this is before approach, no deflection. So, you were essentially somewhere here in the force curve. The laser of course was falling and was going to the center, and this is after approach. So, here is the laser that is coming, and this gets reflected, this gets reflected, and this falls at the position that corresponds to the set point. So, if I may allow to add, so this is the QPD, let us say this is the set point you have. So, the laser goes and falls on the set point. So, this is now it is ready for approach. So, this is more of an imaginative nice cartoon you can see. So, the tip is now in contact with the surface. Here is the laser beam that falls from the laser source and goes to the QPD. Okay. So, before we move on to how it works, first we will, so there are the essentially two important modes in which an AFM can operate. It is the contact mode and the non-contact mode. Now, non-contact mode unfortunately has some limitations, particularly in terms of image resolution. So, it is rarely used in isolation to image, though it has certain advantages. But the more popular one is the intermittent contact mode, which is very popular and is often referred to as the tapping mode. But scientifically you should use the word intermittent contact mode, because tapping mode is a word which is sort of more of a trademark of one particular AFM manufacturer. But in many cases you will find that people are loosely using the word tapping mode, which is also perfectly fine. It refers to the mode of intermittent contact. And then we have the whole lot of secondary imaging modes, which we will also discuss some of them. But your understanding of an atomic force microscope, how it works, depends largely, or you will be able to acquire a reasonably good amount of idea about how an AFM works if we understand contact mode, and that is what we are going to do, at least in this class. So, then we had already talked about the raster scanning operation. So, essentially you identify a zone which can be maybe 500 nanometer square up to let us say 100 micron square. So, AFM scanners have this type of ranges. So, it can be as low as 20 nanometer cross 20 nanometer to 100 micron cross 100 micron. Typically, it is in commercial AFMs it is a square zone, but there are instruments which allows you to scan over rectangular zones also, and then it does a raster scan. So, what is this raster scan? This raster scanning is essentially the tip travels from one point to the other, from one point, every point to point it travels. So, this starts from here, let us say, moves on to the next point, next, and then again it comes back in this direction, comes back all the way back to here, then again moves to the next location and goes like this. So, it is more like performing a nested do loop. So, do I equal to and then again within that So, for every I, let us say this is equal to I equal to 0, it goes to every point from j equal to 0, 1, 2 all the way to n minus 1, then comes back, moves on to I equal to 1, then again moves from j equal to 0 to n minus 1 and something like that. This is a raster scanning, but just think, so typically one would divide this zone into 512 by 512 or 256 by 256 data points. So, now think of a situation, you are not doing some ultra small zone scan, but let us say 5 micron by 5 micron scan area is very common, and you have divided it into 512 by 512 points, or even let us say 256 by 256 points. So, what you understand that the gap between the two subsequent points or two subsequent lines is very, very small. In this particular case, for example, the gap is of the order of 40 nanometer or 20 nanometer, let us say. You can just calculate, just divide 5 micron divided by 256 and you will get the number. It turns out as per my mental calculation, it is close to 20 nanometer. So, how do you really, which motor or which equipment do you use to sort of position this motion from one point to the other? It is very easy to say that, well, you do a raster scan, and but the reality is this is not a computer program you are running to generate some data. The tip has to physically travel to this point and then move on to precisely at the next point, which is 20 nanometer away, then to the next point which is again 20 nanometer away, then to the next point again like this. So, how do you control this? And it is important that this xy motion, because it can be very, very precise and demanding, is also controlled by the piezoelectric scanner. So, most of the earlier atomic force microscopes, they used to come with 3 separate piezos, one for the x direction, one for the y direction, and one for the z direction to control the vertical height. How the vertical height is controlled, we will come to it, but majority of the modern piezos now come with one cylindrical, hollow cylindrical piezoelectric element. So, piezoelectric scanner, you understand what is a piezoelectric material, we have very grossly discussed about it. This is not the right course to discuss about the physics of piezoelectricity or piezoelectric ceramic materials. So, I would strongly recommend you to look into some complementary literature to understand more about a piezo. But very briefly, if you apply a voltage to a piezoelectric material, there is a dimensional change. So, in other words, let us say you apply a positive voltage to a piezoelectric material, it might become longer and consequently thinner, and to the same material, if you apply a negative voltage, let us say, it might become shorter, and therefore, consequently the cross section becomes wider. So, this is what in a nutshell is a piezoelectric element. So, as I pointed out that initial models, they sort of relied on 3 distinct piezos, one for the x, one for the y, and one for the z direction. This is, you can see the tip is mounted to this piezoelectric scanner. This is the AFM tip, but modern instruments have sort of done away with these 3 independent piezos and they use one single piezo. So, this is, we have been telling that the tip is mounted at the bottom of the piezo. So, this is this is more of a cartoon. So, this is like, this is the piezoelectric element, and you have the cantilever holder somewhere over here and the tip is here. The configuration is something like this. So, most modern probe SPMs use a single piezo with tube geometry, and each of the, so it is now split into 4 distinct zones over here. So, this is zone number 1, this is 2, this is 3, and this is 4. Okay. If all the 4 sections are made longer or shorter by the same amount, of course, then you understand that the tip moves in z direction, that is a vertical movement. In contrast, if the, let us say, the x plus side, so this is the x plus side, this is the x minus side, this is the y plus side, and this is the y minus side. So, in contrast, if the x plus side is made longer, at the same time the x minus side is made shorter. How do you make this long and short? It is based on the error voltage that gets generated. Okay. Or so you apply a voltage which can be an error voltage, or if you are rastering the voltage, necessary voltage will come from the software or your computer interfacing, the computer which is interfacing your instrument will take care of this. So, just as a quick look, if the x plus side is made longer and at the same time the x minus side is made shorter by the same amount, the tube deforms a little bit as indicated. It is like this, and for small deformation this makes the tip move primarily in the x direction. The same can be achieved also for y. So, you can see by independently sort of controlling the voltage, you can either use this piezo to move in x or y direction, or you can also make it move in the z direction. Now, soon you will realize when we talk about the operational principle that this rastering thing is more like an independent variable. So, you want your AFM to raster at every point, therefore, it rasters, it travels from one point to the other. So, this voltage that is necessary to make the piezo move along the x y direction is sort of given from the software. It is a software control. So, when you press the scan button, it will give voltages for the movement from one point to the other, or it will give the necessary voltage across the piezo, so that it moves from one point to the other. But as you see that you can also give another type of a voltage input to the piezo, where it sort of all the 4 components, or x plus, y plus, x minus and y minus, sort of made longer and shorter by the same height, so that you have a control over the z. This comes from the topography of the surface and the error that gets generated in the feedback. So, this is what we are going to discuss in the next section. So, this is the rastering. So, you need to understand the rastering motion is a software control thing. It is part of, it is necessary to generate the data, part of the scan, and this is achieved by doing something like this. So, x plus side is made longer and x minus side is made shorter. You may also understand that if this is, let us say, the x direction and this is the y direction, you can also change your loop. So, from instead of I and j, it can be j and I. So, this axis is known as the fast axis and this is known as the slow axis. So, corresponding to the fact that these are the x and y directions, most commercial AFMs will give you the freedom to pick up whether you want to have your x as the fast axis or y as the fast axis. And depending in certain samples, particularly if you have very regularly featured samples like gratings, for example, you need to choose the scan direction or the fast axis or the slow axis depending on the geometry or the feature size, which is also important, and I think we will give you some examples of that. So, the next thing is, so the scanner, just a quick recap on the scanner. So, you understand it is a hollow piezoelectric tube with 4 different zones, each of which can sort of deform separately or in tandem depending on which type of deformation you want to achieve. So, the maximum scan size that can be achieved with a particular piezoelectric scanner also depends upon the length of the scanner tube, the diameter of the tube, its wall thickness and the strain coefficients of the particular piezoelectric ceramic which has been used to fabricate it. Typically, SPM scanners can scan laterally from tens of angstroms, a few nanometer to over 100 microns. In the vertical direction, SPM scanners are sort of limited to up to 7.5 to 10 microns. 10 micron is, I would say, on the higher side. So, majority of the AFMs, the vertical height is limited to 7.5 micron to 8 micron. So, if you have sort of features which are higher than that, let us say you have a feature like this which is 12 micron, the scanner will not be able to cover it and it will generate a profile like this, which will correspond to the maximum range of the scanner, and this is often referred to as the truncation error. Okay. But let us see now how imaging is done in the contact mode. So, let us say that you have approached, the AFM has approached at location 1. So, what is this point 1? It is part of this rastering zone, and let us say it has approached over here at one of the edges. So, this is let us say point 1 where it has approached, and this is the piezoelectric scanner to which the cantilever is mounted. You can understand now a lot of things. You can understand that why the shape of the cantilever is like this, because it is deflected. It is deflected because of the positive because it is in the repulsive regime. The laser light falls, gets reflected gets reflected from the that small tiny reflection zone which is there on the cantilever. The laser light gets reflected and falls at the set point on the PSPD. Now, let us say you would like your scanner to move from point 1 to point 2. What is point 2? Point 2 is, depending on the scan area, if you divide by the number of points, it is the next location where the scanner should go and collect the data. So, let us say from point 1 to point 2 the scanner moves, and there is only deflection of the piezo in the x direction, so that it can move by this requisite amount. So, since there is no vertical deflection, what happens is no vertical the vertical height of the piezo element remains the same at the beginning. So, what happens is, let us say the point 2 is at a higher elevation as compared to point 1. Therefore, since the point 2 is at a higher elevation, the deflection changes, or the force increases. So, let us say the moment you have a change in elevation, the deflection will change, but you can also argue whether point 2, depending on whether point 2 is at a higher or lower elevation as compared to point 1, the magnitude of the force will also increase or decrease. So, what happens is, if the point 2 is at a higher elevation, what happens is that the repulsive force on the cantilever increases, because of the fact that it is now getting repelled by an even larger extent, because it is close. You can see it here, because the tip is in contact with the surface is now closer to the scanner. So, the force increases. In contrast, if the point 2 is at a lower elevation or a lower level as compared to point 1, what is going to happen is that the force is sort of going to reduce. But either way, the moment the force changes, or the extent of deflection changes on the cantilever, immediate consequence is that the laser spot, which earlier was falling at the location corresponding to the set point, now falls at some other location, and immediately an error gets generated. Okay, this is clear. So, from one point to the other, because of the change in topography, there is a change in the extent of the deflection in the cantilever, and we have already argued that the moment there is a change in the deflection in the cantilever, that refers to the fact that the forces have changed, and simultaneously a change in deflection results in a change in the location at which your laser spot had been falling. So, at point 1 the laser spot was initially falling at the location which corresponded to the set point, but from point 1 to point 2, since there is a change in elevation, so this results in a change in the force or the extent of deflection of the cantilever, and consequently the laser spot now falls at a new location. It does not fall on the set point, which is now marked with pink. So, this difference on the PSPD is actually the error. Now, what is done? This error is fed back to the feedback control loop, and depending on whether this error is a positive error or a negative error, this feedback loop now gives an appropriate signal to the piezo scanner, and this signal is in such a fashion so that all the 4 components sort of get elongated or shortened by the same amount, so that the movement of the cantilever, the scanner bottom is in the vertical direction only. So, now what happens? It sort of, for this particular configuration, you would so let us say this was the geometry of the piezo. So, this was the initial configuration at point 1, came to point 2, it became like this. So, the deflection has increased. So, in order to sort of take it back to its original configuration, what needs to be done? The bottom of the piezo has to go up, and this can be achieved if now the piezo or the piezo tube becomes wider and shorter. Okay. So, what happens is, for this particular configuration, the feedback is given in such a way, so that the piezo becomes shorter and wider, so that the deflection now, after the piezo has reorganized itself in the z direction, matches the deflection that corresponded or that was here in point 1, which in other word is the deflection that corresponds to the cantilever after approach. So, every scanning step. So, from this point to this point, you see that it has it is through one or it is through two steps. So, firstly the piezo or the scanner moves at a constant height, right, and then there is an intrinsic error that gets generated due to the change in the deflection, and that error is now fed to the piezo, and then the piezo readjusts itself, so that the cantilever again alters its height now, and the force is back to the same level. So, this is grossly how a contact mode imaging is achieved. So, from every point to point, first the piezo goes to the new point, then checks out what is the error that is getting generated, and based on that error the feedback operates, and that appropriate error voltage is given across to the piezo, so that the piezo vertically readjusts its height. Okay. So, when a sample has an elevation, less separation distance, more force exerted on the cantilever, piezo goes up, we have already discussed it. Sample has depression means from point 1 to point 2. The deflection is converted into change in voltage, and the controller registered in the feedback loop controls the force and distance record of the topography. So, in most cases the voltage applied to the Z electrode Z direction of the scanner at each measurement point constitutes the AFM data. We will discuss this in greater detail. So, this is how contact mode actually works. So, here comes the tip, you have a feature height. So, it sort of goes up and then eventually comes down, and consequently you also understand that at every scan location, every time it moves from one point to the other, means one rastering point to the next rastering point, it actually undergoes two intermediate location. First, there is a motion in the constant, maintaining the constant height or the same height of the scanner, then there is a change in the deflection, change in the force, which results in change in the location of the laser spot from the set point location, and then based on that, that error is fed to the through the feedback loop to the scanner, so that the scanner readjusts its dimension and the level of force is back to the same value as it was after approach. So, at every location the data gets as the data is acquired, the level of deflection goes back again and again and again to the deflection you had set after approach. That is, in other words, it is necessary for the AFM to ensure before it leaves that specific point that the reflected laser beam is falling at the point which corresponds to the set point. So, yeah, that is how it operates. So, this cartoon you can sort of see the tip sort of adheres to the surface and it scans. Typically, there are two modes of contact mode AFM scanning. One is the constant force mode, which we have already discussed. In this mode, the deflection of the cantilever can be used as input to feedback circuit that moves the scanner up and down in Z, responding to the topography by keeping the cantilever deflection constant. I guess you now understand what it means. With the cantilever deflection held constant, the total force applied to the sample also is constant. In this mode, the image is generated from the scanner's Z motion. So, what happens is, you can see here the motion, the Z motion of the scanner is actually now a reflection of the surface topography. So, if you have a surface topography like this, your scanner will also move along in that direction. So, if you can simply track the locus of the Z motion of the scanner, then itself you are through with generating the topography of the surface. So, this is what happens in constant force imaging mode. Constant force mode is very widely used and is very popular and is used for most applications. There is in principle a constant height mode. In this mode, the spatial variation of the cantilever deflection is used directly. So, in this case the cantilever maintains a constant height, it does not change, and therefore, what happens is, depending on the topography from point to point, the deflection will change, and one tracks the deflection to generate the topographic constant. The biggest problem is that your cantilever is short, and if the feature height is very large, it might not be able to capture it. But since we now understand in great detail how the internal adjustment is done in a scanner, we realize that even in constant force mode, the motion actually is split into two parts. The motion from one point to the other is actually split into two parts. First, the motion is at a constant height, and then additionally, so constant height mode anyway is operational, and then additionally what happens is after the first movement has been done based on the constant height mode, then the change in the deflection of the cantilever in a constant force mode is tracked, and according to that the feedback loop sort of operates, and you readjust the vertical position of your scanner, and the forces are back to the same level. So, you can just imagine that if this part of your readjustment based on the vertical direction as well as the feedback loop is somehow made absent, what remains is actually the constant height mode of imaging. Okay. So, then what happens is that once the raster scan is over, so this is a typical atomic force microscope image what you would see. You see some color, but do not be surprised that this has this brown color. What gets generated is actually a data file, which is like x, y and the z position. So, either the vertical position of the scanner or the error voltage corresponding to the set point, okay, either of the two, and this can be, if it is in terms of voltage, it can be sort of transferred or got converted in terms of the topographic height. So, what you have is that this is the grid over which the rastering has been achieved, and at every point, so x and y. So, this is, as we have already pointed out, depending on the direction of the fast axis and slow axis, the tip physically visits every point by point, and it captures the z information at that point. So, unlike any other microscope, which the final product is actually an optical image of the features, here what you get is not any image, but you get actually a data file x, y versus z. So, you get the true z information at every point, and what is done to generate an image like this is to normalize the vertical height and just create a constant contrast in a grayscale or something like that. Based on this normalization, you typically most commercial AFMs will give you a color code like this, and which varies again depending on the feature height. So, you will get images similar to this, but if you have a very rough surface, the maximum scale will maybe read as 5 micron. However, if you have a pretty smooth surface or shallow features, it can be a few hundred nanometers. So, thing to understand, looking at this color scale itself, it becomes clear. So, the darker zones are deep or valleys, and the brighter zones are closer or at higher locations. Remember that in AFM images, the colors are always artificial. This is more of a pictorial representation of a data file. The actual output is the data file. But what is most interesting is this is the only microscope that gives you the actual vertical resolution or vertical information. So, now you can sort of at any location, let us say along this line, you can get a cross sectional line analysis. All you need to do, you need to identify the line at which you want the information. The software typically does it. Let us say this is for j equal to 25, and at every location corresponding to j equal to 25, you have the z information. So, you can very easily get a cross sectional image like this, which no other microscope will allow you to get. So, contact mode, which is the simplest mode, and it is perfectly well suited for hard surfaces or hard samples like metals, for example, ceramics, metals, etc., etc. The advantages are high scan speed, atomic resolution can be achieved with a hard surface. This is the easiest mode to implement. Can image fairly rough samples. There can, and this of course what is not written in the view graph, you must remember that this provides the best lateral resolution, or as it is already written of course there, that it is possible to achieve atomic resolution, but even other than that, even with a routine atomic force microscope without vacuum and anything, seeing a lateral feature of 3-4 nanometer, a quantum dot or a nanoparticle is pretty routine using a contact mode, using the contact mode imaging. But there are some disadvantages also if you are not using a vacuum and you are scanning in ambient. And let me also point out that an atomic force microscope can sort of work extremely well in ambient. You do not need any vacuum or sample preparation or any specific chamber for running an atomic force microscope. There can be capillary bridge formation due to condensation of water from the atmosphere between the tip and the surface of the sample. So, that sort of what happens is then this capillary meniscus sort of becomes the effective tip. You can still get the image, but this becomes the effective tip, and towards the later part of this class or maybe in the next class we will talk about something called tip convolution. So, this capillary bridge effectively increases the size of your tip, and that sort of destroys the resolution to large extent. Since you are actually physically dragging your sample over you are dragging your tip over the sample. So, there is a possibility of damage to both the cantilever, so which sort of can become blunt. The other possibility is that if you are trying to look at a soft sample, instead of scanning, this dragging action, this rastering action can result in scratches on the film or on the sample. So, there is a potential possibility of both sample damage as well as tip damage in contact mode imaging. And so, these are some of the disadvantages. So, the next mode that came into existence was the non-contact mode. I have pointed out that non-contact mode is rarely used, and you will soon realize why. It is rarely used for imaging purpose, but there are some special purpose imaging like electrical force microscopy or magnetic force microscopy to identify electrical or magnetic domains on the surface, where a non-contact mode imaging is used. I mean, but it is often used in conjugation with something like a contact mode imaging, and then by a subtractive mechanism or something like that you would like to dig out different domains. We will discuss some of these techniques probably in the next class. So, then you will have an idea. So, what is done in non-contact mode is the system vibrates a stiff cantilever near its resonant frequency. So, yesterday while in the previous class, while we were discussing about the choice of cantilevers, we also had a criteria about the resonant frequency, and I mentioned that this resonant frequency thing will be critically important when we talk about the contact when we talk about the non-contact mode and the tapping mode. So, here it is. So, the system vibrates a stiff cantilever near its resonant frequency, typically from the range is from 100 to 400 kilohertz, with an amplitude of a few tens of hundreds of angstroms. So, the amplitude is a few tens of nanometer. So, what it does is something like this. So, it is not in contact, it is somewhere over here. It is within, certainly closer to RC, but it is within the attractive regime. And then through an additional drive, it is given a vibration or an oscillation. So, there is now an oscillation with an amplitude, let us say it sort of oscillates between this range. What is done is that it now rasters in this configuration. So, the cantilever is oscillating like this, it is oscillating like this, and simultaneously it is rastering along x and y, along the fast axis and the slow axis. In contact mode, while it rasters, it is in direct contact with the surface. Here it is not in contact. First thing to realize that it rasters, but it is not in contact. And secondly, in contact mode the cantilever was static, but here you apply an additional vibration. It vibrates. So, there is an oscillation like this, but as a part of no part of the cantilever during the oscillation touches the sample surface. It is completely in non-contact. So, the limits of the oscillation ensures that there is a finite gap between the sample surface and the cantilever tip. So, it is oscillating like this between its lower and higher position, or H and L, and in this configuration it sort of moves. Now, what happens is, so let us say this is 0.1, this is 0.2, as there is a topography. So, first thing you have to ensure that you are far away from the surface. So, depending on how rough your surface is, you choose the location where you want to do this imaging. So, what happens is, from this point to this point, since the surface is now closer, this amplitude sort of gets affected, because of the fact that while it is at the lower end of its oscillation, it experiences the interaction or the attraction of the surface. So, this change in the oscillation detects the change in the resonant frequency or the vibration amplitude. So, either the resonant frequency might change or the vibration amplitude might change as the tip surface separation distance changes. Which is actually tracked, and based on that you generate a contrast. So, the contrast which was there in terms of, so based on that you first generate an error. So, again this can be mounted to a piezo, that piezo can sort of move up and down to maintain the level of oscillation or the resonant frequency to its original level, and based on that you can again generate a similar data file as corresponding to what we have done in contact mode. But the only difference is, here the variation in the height was based on an error which was generated on the QPD based on the actual change in the deflection of the cantilever due to a change of force. In a non-contact mode, the error is generated not based on the deflection of the cantilever, but is based on the amplitude, resonant frequency or the vibration amplitude of the cantilever. Important to note, since the cantilever the probe is not in direct contact with the sample. So, the forces are very low, it is of the order of 10 to the power minus 12 Newton, which is grossly 4 orders, 3 to 4 orders lower than the forces you typically would work with with a contact mode. By keeping the resonant frequency or the amplitude constant, the system also keeps the average tip sample distance constant. So, this is what we already said, that the feedback now operates on the amplitude or the frequency. So, the controller sort of tracks the change in the amplitude, that is typically what is done, and when we discuss tapping mode, we will it will be clearer how this change in the amplitude can be detected. Okay. So, this is more important. So, the biggest problem is, so tapping mode is something, or the intermittent contact mode, which sort of takes advantage of both non-contact mode and contact mode. So, the biggest advantage of contact mode is good quality image in the better quality resolution, but the biggest advantage of non-contact mode also has its own advantage, and that advantage is that the chances of sample damage is negligible, because the tip never comes in contact with the sample. So, chances of sample damage during rastering or the tip becoming blunt with progressive usage, both are almost minimal in non-contact mode. But since it does not come in contact, it is sort of this advantages is more than offset in terms of poor resolution. So, tapping mode is halfway in between. You apply this additional amplitude or vibration to the sample tip, but instead of maintaining the sample oscillating entirely in air, what you allow is that as a part of this, so you bring it closer enough, so that as a part of this oscillation, it in one of the ends it sort of touches or taps the surface. Okay. So, it is grossly the same concept that you give an amplitude. So, what happens is you now give a free amplitude. So, after you align, you give a free amplitude, let us say that the limit is L. So, correspondingly on the QPD, now the laser spot sort of travels continuously from these two limits. Okay. So, this is the free amplitude of the cantilever you have given. The frequency that is chosen for oscillation is the resonant frequency. We all know what is resonant frequency. So, you are somewhere over here closer than a non-contact mode operation, but a little further away from contact mode operation, which is purely in the repulsive regime. And what happens is your approach now is with a cantilever which is not only aligned. So, unlike a contact mode approach where your approach started with a cantilever which was aligned, purely aligned, here your approach starts off with a cantilever that is first aligned and then a amplitude is given to it. So, what happens is as the cantilever comes closer and closer to the surface as it is oscillating. So, what happens is at some point it starts hitting or tapping the surface towards this end of its oscillation, and consequently on the QPD, if let us say this was the range corresponding to the free oscillation, the range now gets truncated because it can't go beyond this. So, suppose this was the maximum up to which it should have gone because of its oscillation, but what has happened because the surface has now come. So, this part I will draw a blown up picture, it during the oscillation it touches here and it fails to traverse this part of the oscillation because of the surface. So, instead what it does is it goes on tapping or knocking the surface like this, okay. And this results eventually. So, this is an intermittent contact, unlike a contact mode cantilever where things were always in control, that is not the case, but it is coming in contact. A non-contact mode cantilever would be something like this, it is just oscillating in air, it is never coming in contact. So, here is a non-contact mode cantilever, here is let us say a tapping mode cantilever, okay. And a contact mode cantilever would be coming and straight touching the surface like this. A tapping mode is something like this, non-contact mode is something like this. You give an oscillation. So, non-contact mode, this is let us say the surface you would like to scan, it will scan like this. In tapping mode it will be scanning like this. So, this is the difference. It sort of picks up the essential physics or the operational principle of the non-contact mode scan, but it does an intermittent touching. So, it again feels the sample like a contact mode cantilever, which was completely absent in case of non-contact mode imaging. The non-contact mode imaging, in non-contact mode imaging, the tip was never actually gaining access to the sample. So, what happens is because of this truncation in the oscillation, it can't traverse this part of the cycle, and therefore, there is a truncation. So, I will draw it again in a bigger fashion. So, let us say this is the QPD, this corresponds to the free amplitude, and because it is now truncated part of it. So, this was the let us say the free amplitude in air. Now, the surface comes in. So, this part of the thing gets truncated, and this truncation limits its oscillation of the laser spot by this amount. So, you typically, unlike in contact mode where you set a set point in terms of force, here you would in tapping mode you set a set point in terms of percentage of truncation. Okay. And so, you say that when my signal is 85% truncated, I would stop. Stop means approach ends and piezo and feedback gets activated. Okay. So, now it has reached one location, let us say on the surface where it has approached, where it is tapping with 85% or 80% or whatever is the number you have chosen of its free amplitude, it goes to the next location. Because of the variation in topography, it can be further truncated. So, suppose it was 85% of the free amplitude, this location is closer. So, it is further truncated by some additional percentage. So, let us say it drops now to 78%. So, that 7% additional truncation now acts as the error. So, this error is now fed to the scanner, which now retracts or changes its dimension in such a way. So, in this particular case, the scanner would sort of become fat and short, so that the tip edge can go up and it sets back to the 85% limit again. So, this is how sort of tapping mode works. This is so tip vibrates close to the sample surface, the 5 to 15 nanometer away with an amplitude of 100 to 10 nanometer, and this is this cartoon will give you a nice idea about the tapping mode. Okay, so here you see that this is the movement of the laser path as a corresponding to the free amplitude of oscillation, and so this is far away from the surface, and since the surface is now close, it sort of gets truncated. I would rectify this figure. So, on one side it gets truncated, and this is the error that gets generated. So, first thing is you utilize this truncation to pick up the location or the position at which you would like to accomplish or complete your approach. So, you can specify a instrument will come with an option to say where to stop, and in case of contact mode. So, you will be specifying the force, let us say 3 millivolt force that corresponds to that amount of deflection. In tapping mode or intermittent contact mode, you will be specifying the percentage of the free amplitude at which you would like it to stop. So, this again gives you an idea. So, this is the free amplitude, and here since it is tapping on the surface or due to the confinement imposed by the surface, the amplitude sort of gets reduced, and based on this you set your set point, and then from one point to the other, as the probe moves or the instrument the cantilever moves from one point to the other, there is further truncation, and that generates the error, and this error is given to the feedback loop to generate the error signal, and the piezo sort of then retracts or contracts in the usual fashion, and the data gets generated. So, the final imaging option is very much the same. So, advantages are pretty high lateral resolution, much better than non-contact mode, no damage to the sample and the cantilever tip, can image fairly rough surfaces, and is ideal for scanning liquid surfaces, liquid cells and things like that. Disadvantage, of course, resolution is poorer than contact mode, scan speed is much lower as compared to contact mode, and under liquid, because of the continuous tapping or continuous motion, there can be ripples or local turbulence that can get generated, which adds to the noise. So, in a nutshell, this is sort of an idea what you get about the different modes of AFM. So, this is contact mode, this is non-contact mode. What is missing in this cartoon is that non-contact mode also should oscillate like the one you see over here. So, this is what tapping mode does. So, it sort of oscillates and then moves. This is some sort of comparison between the operating modes. So, these are the critical 3 modes I would now say, though fundamentally I would still stick to my 2 mode or the two mode classification we did, that is the contact mode and the non-contact mode. In contact mode, of course, the first difference between non-contact mode and contact mode is the contact mode, the cantilever is stationary. In non-contact as well as in intermittent contact mode, what you do is that you give an additional oscillation, again driven based on a piezoelectric driver to the cantilever, and it sort of oscillates at its resonant frequency. You choose the amplitude by choosing the motor power or the drive power, and you track this change in the amplitude as a function of proximity of your surface to the tip. In the difference between, but in a contact mode there is no hardware to give any fluctuation to the cantilever cantilever. So, it is stationary, it is directly stationed on the surface, it operates in the purely repulsive regime, as you can see here. In contrast, the non-contact mode operates furthest away from the surface, but important thing to note is all the modes operates only when you are at a zone or at a location where you have active interaction. So, none of the AFM modes can operate here. So, that is not possible, because you need to have the atomic interaction or the forces in place for an AFM to operate. Then some of the limitations of contact mode are sort of taken care of by the non-contact and the intermittent contact mode. So, particularly for polymeric material or soft materials, one would preferably not use the contact mode, because what happens is that the tip is sort of, during the rastering, tip sort of drags along the surface, and then there is problem of scratching. So, one would go for a contact or intermittent contact or a non-contact mode. So, now the standard practices are to use either contact mode or a intermittent contact mode. So, here are the details which are sort of already I have discussed. Non-contact mode also exists, but is rarely used for imaging, and is, of course, we will see that in some special cases it is used. So, this is the operating principle of an AFM, but one has to be very careful, because the image you are seeing is sort of a rendered image. It is not a true image, that is, you get an x, y versus z data, and which is then transferred to sort of an image, so that it can be understandable to the user. One major thing is that the resolution of the image, to a large extent, as we have been repeatedly telling, the resolution of the image to a large extent is a function of the tip size, because you can understand that if you have a feature like this and your tip is wide like this, what you will see is a large feature like this. Or if you have a deep trench like this and you have a tip which cannot go in because of confinement or fouling over here, the effective geometry you will see will be something like this. So, this effect, I mean, I would say that it is some sort of an artifact that sort of gets generated because of the geometry of the tip to a large extent, which can be because of the some geometrical dimensions of the tip are comparable to the feature size. That can be one of the problems. The other problem is that during operation the tip has sort of become blunt or something like that, or your tip is too large as compared to your feature size. It is not that if you are trying to scan a 5 nanometer feature with a tip which has a tip radius of curvature of 20 nanometer, your instrument will fail to scan. But what you need to understand, that with a 20 nanometer tip you can't really scan a 5 nanometer feature. What you will get will be, there are some complicated relations, I am not going into it, but what you will get will be much larger than that, and the artificial dimensions what will come out will be sort of to a large extent dependent on the geometry or the radius of curvature of the tip. So, this is in order to tip convolution, it is extremely important that you have some bit of idea about the surface you want to use or you want to scan, and you get appropriate tips. So, if you are, let us say, trying to scan surfaces with deep trenches, it is better to go for high aspect ratio tips. Interesting thing to remember, or important thing to remember, is that here unlike any other microscope like a scanning electron microscope or an optical microscope, the feature size is not limited by optical diffraction or the diffraction of the illumination source, but to a large extent the feature size is limited by the tip size or the radius of curvature of the tip, and in certain cases it can also be a function of the height of the tip. Height is an important parameter that comes in over here in an atomic force microscope, because no other microscope can give you any idea about the height of the features. AFM can sort of scan almost any type of surfaces. Of course, we mentioned in one of the previous slides that the vertical range 10 micron. So, it can't scan features which are rougher than that. Of course, it can scan, so but if you have a very rough feature, the image you will get will be sort of something like this, again some sort of an artifact. This is a truncation artifact that will come in. Okay. So, you have to worry about this thing, but only one type of feature it cannot scan or generate the true images, and they are the reverse tapered features. You need to understand that if you have some features which are like this, your AFM will not be able to scan, and you may want to think what would be the likely geometry. You will get something like this, because a tip, since it is coming from one position to the other, it will pick up, it can't pick up 3 different heights of the sample corresponding to the one single I and j. So, please remember that though AFM is extremely versatile, reverse tapered features or hollow features or something like that, it is not possible. So, if you have some hollow features like this, let us say, your AFM will only pick up the surface feature. So, with that we come to an end of this particular class. In the next class, I will take up some of the additional imaging information or additional informations that can be extracted from an AFM as a part of its scan, which are sometimes referred to as the secondary imaging modes. Thank you.